Okay, hello everyone. Welcome to the lecture on analog interflow network coding. My name is Dong-ho Yu, working in ComNet as a postdoc. From the last lecture, maybe you learned about digital interflow network coding. So in this lecture, you can learn what is the analog interflow network coding, and you can check what is different from the digital interflow network coding. Okay, this is the contents of the lecture. First, let's see the motivation of analog interflow network coding. Then I will conceptually explain the physical layer network coding, analog network coding, and the software-based network coding. Unfortunately, since this lecture is just assigned for only one time, I cannot address the deep technical parts. That's why I want to explain you just fundamentals, basics, and concepts. Maybe you can understand about it easily. Okay, let's see the motivation first. What do you think about network coding? What do you think network coding is? Actually, this is very important to avoid the confusion between the digital network coding and analog network coding. According to this paper, the network coding is a coding at a node in a network. Actually, this is very simple, but we need one more thing. What is the coding? If network coding is coding at a node in a network, then what is the coding here? I can say this is the series of the process to convert information into another form or representations. So consequently, we have to think that network coding is not limited to the XOR operation. Since we learned digital network coding first, many people can think like that. Most conventional network coding are operated in higher layers, such as transport and network layers. There are some people said this is the packet-based network coding actually. Therefore, these network coding schemes use the packets to encode and decode it. However, for the analog interflow network coding, such as physical layer network coding and analog network coding, are operated in the physical layer. That is, they use symbols and signals for the network coding. Therefore, the original XOR operation cannot be used in the physical layers network coding and the analog network coding. Okay, this is the block diagram of the physical layer. There are channel coding here, modulation, OFDM, and so on. Among these blocks, if the node makes a network calls, this can be on analog interflow network coding. Consequently, the analog interflow network coding is the network encoding and the decoding that processed between the physical layer blocks. Good. Okay, now let's see the physical layer network coding first. As we guess in this name, this is the one of the network coding operating in the physical layer. Let's consider the two-way relay channel first, in which two nodes want to communicate with each other with the help the relay node here. Okay, this topology also known as Alice-Bob topology. For simplicity, let's change the node name into the node 1 here, and node 2, and node 3. Here, node 2 is the relay node. When use straightforward scheduling without the network coding, node 1 transmits the data to the node 2 in the first time slot. And then the node 2 relays the data to the node 3 in the second time slot. After receiving the desired data, the nodes retransmit on data to the node 2 in the third time slot. Then node 2 relays the data, node 1 in the first time slot. Therefore, to complete the transmission, 4 time slots are required in the straightforward scheduling without network coding. Okay, next, let's see the straightforward network coding. Similarly, in the first time slot, the node 1 transmits the on data to the node 2. And in the second time slot, node 3 also transmits the on data to the node 2. Then node 2 encoded the received data using the exclusive over here and broadcasts the encoded data, the S2. Therefore, since node 1 has the on data S1 here, the desired data S3 can be easily extracted by XOR operations. Similarly, since node 3 also has the on data S3 here, the desired data S1 can be easily extracted by the XOR operations. Therefore, in the case of the straightforward network coding, 3 time slots are required to complete the transmission. Since this reduces 1 time slot than the previous case without network coding, 33% of throughput can be improved. Finally, let's see the case of the physical layer network coding. In the first time slot, the node 1 and node 2 transmit the on data to the node 2 at the same time. This is the main difference. After that, node 2 encodes the superposed data somehow and then relays to the node 1 and 2 in the second time slot. Using the relayed data from the node 2, the node 1 and node 3 can extract their desired data somehow. Here, the important thing is that how to do the network encode in the node 2 without separate reception of S1 and S2. Actually, this is the very important. Okay, now let's see the details. Anyway, since the physical layer network coding can reduce 2 time slots than the first case, only 2 time slots are required to complete the transmission. Therefore, 100% of throughput can be improved, the straightforward case without network coding. And 50% of throughput can be improved, the straightforward network coding case. Okay, let's see more details later. Okay, then let's see the details of the physical layer network coding. However, in order to understand the physical layer network coding, we should know about the digital modulation first. As you know, the digital modulation is a mandatory part in the modern digital communication system, such as LTE. It converts the bit stream that comes from higher layer into symbol signal. This considers as the first step to convert digital signals into analog signal before RF transmission. There are many modulation schemes, but these 4 modulation schemes are very well known. First, FSK, frequency shift keying, ASK, amplitude shift keying, PSK, phase shift keying, QAM, quadrature amplitude modulation. Among them, modern communication systems use the PSK here or the QAM only. Okay, let's see the example of the binary PSK first. Yeah, it's called BPSK. There are 2 symbol cases here, -1 and +1. If we transmit the binary 0 here, it is mapped into the +1. And similarly, if we want to transmit the binary 1 here, it is mapped into the -1. Yeah, and of course, you can change the mapping rule, like binary 0 is -1 and binary 1 is +1. Yeah, you can choose one of them. Since the BPSK is just one-to-one mapping, that's why it transmits 1 bits at one time slot. However, if we use the orthogonality of the sine and cosine wave, we can transmit the 2 bits at one time slot with the same error performance with the BPSK. Simply, the orthogonality means there is no any interference and no conflict between sine and cosine wave. Therefore, like the equation here, like these equations, if we multiply the two signals by cosine and sine separately, we can make one QPSK symbol signal that includes 2 bits. Okay, then let's back to the example of the straightforward network coding. In the first time slot, the node 1 transmit binary 0, 1. Okay, let's assume that. Then node 3 transmit binary 1, 1 in the second time slot. Then node 2 does the XOR operations and relays back to them 1, 0 binary. So node 1 and node 3 can extract their desired bits using the XOR operations. Yeah, it's very simple. So now let's see the example of the physical layer network coding. In the physical layer network coding, before transmitting, the bits are modulated into the symbol signals based on the modulation table here. So the binary 0 is +1 and the binary 1 is -1. As I said, the QPSK used the orthogonality to basis, cosine and sine. It's totally independent even if we transmit two symbol signals at the same time. Yeah, anyway. So the node 1 and node 3 transmit their own symbols to the node 2 in the first time slot. When we use that, there is no error when you assume that the node 2 will receive the superposed signal 0 and -2. If they transmit +1 and +1, it's +2, right? And if node 1 transmit +1, node 3 transmit -1, it will be 0 in the relay node. -1, +1, 0. -1, -1 is -2, right? So if we indicate the proposed symbol as an equation, it's like that here. Yeah, S1 is the symbol from node 1 in the T timetable, and the S2T here is also the symbol from the node 2 in the time T. Here S1 is A1 cosine omega T minus B1 psi omega T. Similarly, S2 is A2 cosine omega T minus B2 sine omega T. And when we use the associative law, the proposed symbol can be simplified like this: A1 plus A2 here and B1 plus B2. Actually, this is very simple. Anyway, after receive the proposed symbol signals, the node 2 does the remapping based on the table here. Yeah, if the proposed signal is +2, it's remapped into the +1. If the signal is 0, it's remapped into the -1. And finally, if the proposed signal is -2, it is also remapped into the +1 in the relay node. and the node 2 relays the remapped symbols to the each destination node in the second time slot. Then the node 1 and node 3 also superpose the received signal with their own signal. And then, based on the mapping rule, as I explained, they do the ramping like in the relay node. So the 2 here, right? 2 is 2 into +1 and 0 into -1 and -2 into +1. Yeah, and finally they demodulated the symbol signals into the bits. Even if it seems to be complicated, actually it's very simple. When they know the mapping rule, yeah, it's very simple. Anyway, therefore, they transmit and receive 4 bits during only 2 time slot. Okay, now let's see the idle performance of the physical layer network coding. Since we didn't consider the critical issues such as synchronizations, errors, that's why I called it the idle performance. Anyway, the left one is the bit error rate performance of the received bits, and the right one is the effective throughput performance. Here the QPSK is the case without network coding, and SNC is the straightforward network coding case, and PNC is the physical layer network coding case. As you can see, the BR performance is almost the same, right? However, the throughput performance is totally different. It is calculated by 1 minus BR multiply RS. Here, RS denotes that the maximum data rate. For instance, when the node 1 and node 3 exchange 2 bits respectively, the transmitted bits are 4, right? So this transmission is over in 2 time slot, right? So it's 4 divided 2. So its RS is 2. Anyway, the PNC outperforms no network coding case by about 100% here. And the PNC outperforms the SNC case, straightforward network coding case by about 50%. In summary, PNC is outstanding when we use the mapping rule in the physical layer. That's it. However, there is a chronic problem when we use the QAM in the physical layer network coding. As I said, the QAM modulation is very popular modulation schemes in the modern communication system. Let's see the example of the 16 QAM. Actually, it is the same to use for ASK in the 2 independent bases, cosine and sine. Therefore, if we consider only one basis, cosine or sine, the constellation is like this. And the 2 nodes transmit the symbol modulated by this constellation for ASK. The superposed symbol will be like the below constellations. -3, -3 is -6, right? And -3 and -1 is -4. And -3 plus 1, -3 and plus 1 is -2, right? Anyway. -3 and plus 3 and 0, -1 is -2. and -1 and +1 is also 0, and +1 is +2, and +1 +3 is +4, and +3 is +6. Yeah, did I miss something? Yeah, it's so confused. Anyway, yeah, there are 7 superposed constellation in the relay node. However, there are some ambiguous constellation. For instance, let's see the -2 here. For the -2, there are only 2 cases, -3 and +1 is -2, right? And -2 and -2 is also -2, right? So symbol -3 is binary 0, 0, and +1 is binary 1, 1. So when we do the XOR operation, it's binary 1, 1, right? And another case, -1 is the binary 0, 1. And so -1 and -1 is binary 0, 1. XOR the binary 0, 1, right? Yeah, 0, 1, 0, 1. Yes, right. So since this is the same, yeah, the proposed zero bits is the 0, 0. So when we relay the node to receive the proposed symbol -2, since there are 2 binary cases, 0, 0 and 1, 1 here, so it's hard to do the remapping in the relay node. Yeah, therefore it is so hard to use the co-modulation in the simple two-way relay channel, yeah, also known as RSPOP topology. However, there are some solutions to overcome this problem. Let's consider the butterfly topology using one relay node. The 2 sources here, S1, S2, want to transmit their own data to the destination node, D1 and D2 respectively. However, let's assume that the distance is so long, so they need the relay node in the middle. And the D1 is relatively closer. D1 is closer to the S2. And similarly, D2 is also relatively closer to the S1. So they can listen their transmitter signal directly. But it's not the designer signal. So it's the interference signal for them, actually. Yeah, right? So, and the next time slot, each destination node receives the proposed symbol signal from the relay node. However, they already have the interference signal. They can use the signal somehow, even if the interference. Okay, let's see one example. Let's assume that the S1 transmit +1 here. That is the binary 1, 1. However, this is not the desired signal of the D2, but D2 store it to use later. And when the D2 receives the proposed signal from the relay node, the first D2 check what I already have. If D2 has the +1 here, only these 4 constellation points were transmitted by S2. In other words, these 4 points are the candidates affected by the non-symbol +1, right? But the D2 received the proposed signal -2, so the desired symbol is -3 that transmitted by S2. This is also the node use the same mapping rule. The problem of the using co-modulation can be solved easily. Okay, yeah, actually this is the end of the physical layer network coding. So next, let's see the analog network coding. That is the simplified and modified version of the physical layer network coding. Okay, see you.